This is the pre-lab lecture for activity 1, where we're going to be practicing graphing. You're going to be graphing manually as well as using the program Excel to graph. And we're going to go through one example here for you. We're going to talk about a graph between the two properties of temperature and pressure, which is very similar to the first graph you're going to be making today, but I've changed the numbers a little bit, so my graph will be different than yours. If you're going to manually make a graph, then you're going to have two different variables. One of the variables is going to be what's called the independent variable. This is the one you set. If we're doing an experiment, you might actually set a water bath at 50 degrees or 100 degrees or 200 degrees. So you control that particular variable, and then you measure something else. So we set the temperature, and in this case, we measure what the pressure is, and so that pressure is dependent upon what temperature we set. So it's called the dependent variable. And when you make a graph, the independent variable, the one that you control, goes on the x-axis, and then the one that varies, the one that depends upon that, goes on the y-axis. So if we're going to make a graph, you're going to want to make a title. I'm not going to put one on here for you, but you can think about what you might want to use for the title. The activity gives you some suggestions for that. And we've got to now spread out values along the horizontal axis, which is our x-axis, and spread out values on the vertical axis, which is our y-axis. So when you make a graph, particularly on a piece of paper, what you want to do is you actually just don't want to take the numbers that are given, like 50, 100, 200, 300, 400, and just write them evenly spaced along the x-axis. Watch why this is bad. If I start here at 0, this is 25, 25 more, 25 more, 25 more, and now look, 50 more, 50 more, 50 more, 50 more. You can't have a graph where the divisions are unevenly spaced. So this is the most common error people make when they're doing a graph. They just take their numbers and they put them across the bottom axis there, and they may not be evenly spaced, so don't do that. Now, if I do it like this, each of my divisions represents 50 Kelvin, 50, 50, 50, 50, 50, which is lovely. That's been done well, but here's the problem with this. All the data points are going to fit in this shaded region here. I'm using less than 50% of the graph paper, which means the graph's going to be smaller than it could be, and the smaller a graph is, the harder it is to read it accurately. So this is not a good way to spread out the temperature values on the x-axis either. I could maximize the space and put the lowest value at the very left, 50, and the highest value at the very right, 450. That way I'm going to spread all the x values out completely along the horizontal axis. But the problem with this is if you figure out what each division is going to be, every division turns out to be 18.18 Kelvin. So if you go 5 divisions over, it's 140.9. And if you go 5 more divisions, it's 231.8. And when you have divisions that are really strange numbers like that, it's hard to plot 100 Kelvin and 200 Kelvin. So that's not a good idea either. You actually want to try to use as much of the graph as you can, but you want the divisions to be convenient numbers. So something like this might be better. Each division is 25. You go 4 divisions, you get to 100, another 4 to 200, 300, 400, 500. And so we're not using 100% of the graph, but we're using a good deal of it. So this is probably the more ideal way to spread out these particular temperature values. We're going to use the same technique on the y-axis here. Now our values only range from 0.1 to 0.9, so I'm going to make the divisions significantly different. Each division is going to be 0.05, and if I do that, I can go from 0 to the bottom up to 1.1 on the top, and I'm going to spread my pressure values out almost the entire y-axis. Notice the divisions on the y-axis do not have to equal the divisions on the x-axis, right? The y divisions are 0.05 atmospheres, but the x-axis, they're 25 Kelvin, so they can be different from each other. And there's no rule that says you have to have the very first number on each axis be 0, but if you want to see what the origin is of the graph, if that's important, then that's why we would do that. So you're going to plot each of the coordinate pairs, temperature, pressure, coordinate pair for all of them, and you're going to get a graph like this. And if the data is supposed to be linear, then what we're going to do is we're going to try to draw what's called the line of best fit through the data, which would be really lovely if the line went right through every single point. But when you're dealing with experimental data, sometimes that's not the case. So when you're doing this manually, you have to try to draw a line that is as close as possible to as many of the points as possible. And that might be a line that looks like this. I can make my line touch like 5 of the points, couldn't quite get it to touch this one here. But that's what happens. Sometimes it's not going to be perfect, but that's why it's called the line of best fit. Now, what you want to do with your line is you're going to want to report what its equation is. And the equation for a line is y equals mx plus b, which means you have to tell me what m is, the slope, and you have to tell me what b is, which is the intercept. We'll leave y and x as variables. So the way you get a slope is difference in y's over difference in x's. So we're going to calculate this. And to calculate this, you want to pick 2 points on the line and then subtract their y coordinates and then subtract their x coordinates and divide those. Now, it's always best not to pick the actual points you plotted. Try to find some very convenient points along the line, usually one way to the left, the other way to the right. So here's one way to the left. It's exactly on the 75 Kelvin vertical line. So that's going to be easy for me to know my x value. It's going to be 75. And then way up here, I know this is at 425 Kelvin. That's easy to read. So I've got my x values easy. I'll just have to read what the y value is that corresponds. Now, when you calculate a slope, because the x and y axes have units, the y-axis is atmospheres, the x-axis is Kelvin, your slope's going to have units, and I'm going to want to see the units on that. So now if I subtract my y values, it looks like they're about 0.940 atmospheres for that high point and about 0.174 atmospheres for the low point. I'll subtract those, and my numerator will have the units of atmospheres. And then the difference in the x's are going to be the 425 Kelvin minus the 75 Kelvin. And so when I get my answer, it's going to come out to 3 significant figures, 0.00220, and the units are atmospheres per Kelvin. So now I have the slope. The second thing you need to determine to get the equation for the line is its y-intercept. You can do this graphically by extending your line until it crosses the y-axis. So when you extend a line past your last data point, we usually use it in dotted form. And wherever it crosses that y-axis, that's going to wind up being its y-intercept. That could be, let's see, 0.01 or something, I don't know what that is. It's pretty small, 0.01, something like that. A better way to do it is actually algebraically by using the equation for the line, y equals mx plus b. We just determined what the slope was, 0.00220 atmospheres per Kelvin. So you pick one point on the line, and I'm going to pick that red point at the very top. The y value is 0.940 atmospheres, and then the x value is 425 Kelvin, and then you solve this for b. And if you move things around, b turns out to be 0.005 atmospheres, which is way more accurate than me trying to read that graph because it's just so small and down there at the corner. So therefore, you've now determined the equation of the line. You would express it y equals 0.00220 atmospheres per Kelvin times x plus 0.005 atmospheres. Now, you're going to make a couple of other graphs today, but it's not going to be manual graphs. You're going to use Excel. And Excel is a Microsoft program. And if you do not have it, it is offered free to all Saddleback College students. You go to this particular website, and you can actually use all of the Office suite, which would include Word, Excel, PowerPoint. And so if you don't have it on your own computer, you can actually use it here, and you can get it on your computer. So the way this works is, if you're going to use Excel, you open up an Excel spreadsheet, and you're going to make a column for your X values and a column for your Y values. Now, I've got them in columns. You could actually do it horizontally as well. You just put the X values on top and the Y values below it. So it can be vertical or horizontal. So I've done it vertically here. So I put my X values first, my Y values second. And then what you do is you select all the cells that you want to graph. And then up near the top where it says insert, you click insert, and it'll give you a choice of different types of charts. You're going to want to pick a scatter chart, and you click that. And then as the procedure of the activity tells you, you can click a couple buttons, and it'll actually put the equation of the line right on the graph for you. And you're going to see something like this on your Excel spreadsheet. So you can see I've got the points plotted. I've got that second point down there that was a little bit off the line like we did when we did it manually. And it's expressed for me, the equation of the line right on the graph, y equals 0.0022x. That's what we got about right. But it says minus 0.0024 as the intercept, which is different from what we had. It actually calculates specifically with linear regression what's the line that's closest to all 6 of those points. And if you do that, that actually changes where it crosses the y-axis. So if you have the best fit line, the intercept turns out to be negative 0.0024. So this is actually how we use Excel to make a particular graph. Now, whether you're using Excel or whether you're plotting manually, once you have an equation for a line, I'm going to want you to be able to use that equation. And this is going to be an example of a type of question you're going to have to answer. Let's say I ask you to find the temperature when the pressure is 0.750 atmospheres. So if you have a manual graph, you can do this graphically. You know the pressure is 0.750 atmospheres. Go onto the y-axis where pressure is, find 0.750, and read over to where the line is. Find that point on the line, and then you read down to where the temperature is. And it looks like that temperature comes out somewhere around, I'm guessing, maybe 338 Kelvin. Now, you might feel a little worried about that. That's a little bit iffy. A better way to do it is to use our equation. And so I'm going to ask you actually in the activity to do both read it graphically and then calculate what this value would be from your equation. So algebraically, we're going to use y equals mx plus b. We know the m value, 0.00220 atmospheres per Kelvin, and we know the intercept, 0.005 atmospheres. So what we're going to do is we're going to plug in the y value of 0.750 atmospheres, and we're going to solve for x. And so if you can manipulate this equation to calculate x, x comes out 339 Kelvin, and that's how you're actually going to be able to read this graph. So with that said, you have one graph to plot manually, two graphs to use Excel. When you make your Excel graphs, actually, you're going to actually have three graphs altogether. But when you make your Excel graphs, you can either print them out, and then you'll need to take pictures of those in order to submit them along with your lab report. Or if you want to take a picture of the computer screen, I would accept that as well, just so I can actually see the graphs that you've prepared on Excel.